In this video, we're going to cover a couple of functor properties relating to limits in categories. So the first property is preserving limits, and the second property is reflecting limits. And each of these two definitions has both a small and a non-small version. So the way it's going to work is if it's the small version of either one, we read everything, including what's in parentheses. And if it's the non-small version, then we just ignore everything in parentheses. So for example, let's take a look at the first definition. So let's look at the non-small version first. So we're not going to read anything in parentheses relating to anything being small. So a functor f going from a category C to a category B preserves limits if any time a diagram D going from an index category J to a category C has a limit L, so this is curly L, which consists of the vertex L and then each of the legs to each of the objects in D, then f of L, so that's the image of that cone under some functor f that we've defined, has to be the limit over the image of the diagram. And that's what we have here. We have our diagram D in our category C with a limit L over it. And then all of that gets mapped by our functor F into the category B. And we need to have that this cone here, the vertex FL and the legs FLJ, these ones here, need to be a limit over this diagram here, which is where we map D by our functor F, which is also another diagram, right? Because every diagram is just a functor and every functor is just a diagram. Now, what is the small version of this definition? Well, it basically just says that this applies anytime we have a small diagram D, which means that the index category J, the objects in this index category form a proper set. It's not big enough to form a pure class. So we can read it with the parentheses this time. So a functor preserves small limits if anytime a small diagram D has a limit L, then f of L is a limit over f after D, sorry. So that's the small version. It's pretty simple. It's just basically saying this only applies when the diagram D is a small diagram. So that's preserving limits. Now what about reflecting limits? So for the non-small version, a functor f, again going from C into B, reflects limits if any time L, so this same cone L here, is a cone over a diagram D, such that the image of that cone in B is a limit over the image of the diagram, then L is a limit over this diagram. So you see what it's saying, right? The first one was just saying, if this is a limit, then it must be a limit after we apply F. And this is saying, if after we apply F, the image is a limit over the image of the diagram, then it gets reflected back, right? It comes back, and this L cone here is also a limit over this diagram D. And again, for the small version, we basically just say that this applies to small diagrams. So a functor f reflects small limits if any time L is a cone over a small diagram D, such that the image of L under F is a limit over the image of the diagram, then L is a limit over D. So it's basically just saying this applies only when J is a category where the objects form a proper set. So let's look at some examples for these. In this video, we'll look at an example for preserving limits, and we'll look at an example for reflecting limits. And then in a separate video, I'll include sort of like a challenge exercise that covers both, and some topics from some other videos, previous videos. And for each one of those exercises, you can pause the video and try the exercise. If you don't remember some of the definitions, you can keep watching and I'll sort of provide all the definitions up front. Then you can try pausing the video again, see if you can complete the exercise. And then after that, I'll show you how to solve those examples. So let's actually start with the reflecting limits one. So our first example says that fully faithful functors reflect limits. So go ahead and pause the video if you want to try that. Or if you need a reminder, a fully faithful functor is a functor that is both full and faithful. So what that means is that every home set in C here is mapped bijectively by the functor. So if you take any home set in C, then when it gets mapped by F, the morphisms that it gets mapped to in this home set on this side needs to be a bijective mapping. So say we had like A and B in C and had a couple morphisms between them. Then when we mapped it by F, if it was fully faithful, we would need to have two morphisms on this side as well, going from FA to FB, so that this morphism part of this mapping is bijective. So to prove this, suppose F from C to B is fully faithful. And suppose that D goes from J into C, it's a diagram, and has a cone L, which consists of a vertex and legs LJ for every J and J. And suppose that the limit of the diagram that we get when we apply F to our diagram D, so that is F after D, is actually F of L. So it's the image, just like we showed, or just like we explained for the definition. This image here is a limit over the image of this diagram. Then what we need to show is that it reflects that limit. So this cone here is actually not just a cone over D, but it's actually a limit over D. So how do we do that? Well, we need to show that if there's some other cone with maybe vertex X and legs XJ for each J, that there's a unique mediating morphism going from X into L such that all of the legs commute, right? It's a cone morphism going from this cone to this cone, and shows that L is a terminal cone. So we have that L is a limit. So now suppose X, which consists of a vertex X and legs XJ for every J and J, is a cone over D. Well, then if X is a cone over here, then F applied to X, so that's going to be F of X, and then the image of these legs here, that is also going to be a cone over the image of this diagram, right? Because functors preserve cones always. And if you don't believe me, you can quickly prove that yourself. That should be like a 3-line proof. Prove that if X is any cone over any diagram, then the image of that cone under any functor will be also a cone over the image of the diagram. So if that's the case, then we know that f of x is a cone over f after d, right? The image of the diagram here. And if that's the case, then we need to have our unique mediating morphism. So there exists some theta going from f of x to f of L here. Such that FLJ after theta is always equal to f of xj, right? It commutes, all of the legs of this cone commute with all of the legs of this cone by theta. It's a cone morphism. And this is for all j in J, that is for every leg. Each leg of this cone X commutes with each leg of this cone L. And if that's the case, we know that the functor is fully faithful. So that means there has to be, because the morphism mappings are bijective, there has to be exactly one morphism in C that maps to this theta, right? So there exists some unique U going from X to L, so like some U here, such that f of U is equal to theta, right? There has to be one because it's surjective, and it has to be unique because it's injective. It's a bijective mapping. But then for all j, we can substitute fu in for theta here, so we get f of lj after f of u is equal to f of xj. And since these are functors, we can combine these and just say that this is f of lj after u, and this is equal to f of xj. But remember again that this is fully faithful. So that means that if we have f of something equals f of something else, we know that the insides have to be equal, right? Because it's an injective mapping. So this implies that lj after u equals xj. And that's for all j. But that is exactly the commutativity property we needed for this to be a cone morphism, right? So we've found a potential cone morphism going from X to L. Or I should say a potential mediating morphism. It's not a potential cone morphism. It definitely is a cone morphism, but we need to show that it's a mediating morphism. So we need to show also that it's unique. It's the only morphism that allows these legs to commute with each other. So in order to show that, suppose that there exists a u prime such that lj after u prime also equals xj for all j and j. Then, if that's the case, we can apply f to both sides to get f of lj after u prime is equal to f of xj. But if that's the case, then we have to have that we can split this up. So we can say that f lj after fu prime equals f xj, which means that theta has to be equal to f of u prime, right? Because theta is the only morphism that makes this equation true. but f of u prime also makes this equation true. So it has to be that theta is equal to f of u prime, but theta is also equal to f of u, we said. And according to this one, right? But then we can apply that f is fully faithful again, right? The third application of that. And that is that if f of something equals f of something else, then the insides must be equal, right? So we have that u equals u prime, which is exactly what we needed to show, right? That shows that u is unique. It's the only cone morphism going from x to L over the diagram D. And so that is QED for this example. So let's move on to the preserving limits example. For our second example, we need to show that the covariant home functor preserves limits. So go ahead and pause the video and see if you can show that. This one is a little bit more difficult. And if you need a reminder first, the covariant home functor fixes some object A in our category C, and then you can define the covariant home functor home A blank, which goes from our category C to the category of sets, so it's a set valued functor, and it's defined by when it takes in an object, some C in C, it basically just fills in this blank here. So we get home A C, right? Takes in an object in C and returns a set, namely the home set from A to C. And when it takes in a morphism, say F going from C to D in our category C, it gives us back the follow by f function, which takes in morphisms in the home set from A to C and returns morphisms in the home set from A to D. And follow by is just defined pretty obviously. It's just defined by follow by alpha for some alpha in the home set from A to C simply follows that morphism by f, right? So it's f after alpha. So to prove this, let D be a diagram going from J into C, and suppose that the limit of D is L, which is here, consisting of L and the legs Lj for J and J. Now we need to show that this home functor preserves limits. So we need to show that the image of L under the home functor here, the covariant home functor, is also a limit over this diagram, home A blank after D. So what we'd need to do is we'd need to show that if there was some other cone over this diagram here in the category of sets, maybe call this one W. So W is an object in the category of sets, which means it's a set. And so suppose that W and then the legs Wj for every J and J. And where do these legs go from? They go from W into the home set, the home sets where A is the codomain, right? So this would be home, the domain is A, and then we want the object associated with the jth object in J. So that would be dj. Suppose that forms a cone over home A blank after D. Well, remember that W is a set in the category of sets, so it makes sense to talk about elements of W. So let's fix one element of W, maybe call it X. Then what are these mappings? W, J, for each J in our index category. Well, they take an element of W, like an X or something like that, and they return a morphism going from A to whatever object we're talking about, so some dj. This should actually be home D of M, home from A to D of M, I should say. And same for this one. This should be home A D of N. Now X in W is going to map to a certain morphism in each home set here, right, in this diagram. So what happens if we take the collection of morphisms that X maps to, one out of each of these home sets? Well, we'd have a collection of morphisms where each one had domain A, right? That's the domain for all of these. And then one for each dm as codomain, right? But that kind of sounds like a cone, right? It kind of sounds like A and then all of the wj of x's specifically, right? So when I take an element of W, I get back a morphism going from A into D of J, and this is for all J and J. So what is this? It's our source object for our covariant home functor A, and then one morphism going from A into each of the DJs, right? So the question is, it looks like a cone, but what do we need for it to be a cone? The legs would have to commute with the morphisms in this diagram here, right? Like these D alphas. But we do know that we have that commutativity property over here, right? Since this is a cone for sure. So what we can say is that for any alpha, like this one going from M into N in J, we know that we have this commutativity property, so that's followed by D alpha after WM is equal to Wn, right? This triangle here. But if that's the case, then we can apply this whole thing to X specifically in W, and we'd get followed by D alpha applied to Wm of X has to be equal to Wn of X. And then if we just apply our follow by, it just gives us back that D alpha after Wm of X is equal to Wn of X. And so we have the commutativity property that we need, right? Any of these D alphas commute with all of the Wm of the X specifically that we're talking about in this collection. So this is a cone over D since this argument. But then if this is a cone over D, then we have a limit over D, right? L here. So we must have a unique mediating morphism going from A to L. So there must be some unique mediating morphism, maybe we'll call it phi, going from A to L, And this phi corresponds to this x, right? Because it's that collection that we're talking about for this specific x. So we could maybe even subscript it with that x. And that phi is such that basically all of the, so this is our phi here, all of these legs commute with all of the legs of L through phi, right? That's what it means for this to be a cone morphism from this cone to our limit. So that is such that Lj here is equal to, or Lj after phi of x is equal to Wj of x. And that applies to all of the legs for all j and j. So what we have is that for any x, if we pick one x in W, we can find one unique mediating morphism phi that makes this commute based off this construction here, right? This is all of the legs of this cone, which are the specific morphisms that get picked out when we apply x and follow it into each of these home sets. But since for each x there's a unique morphism, that means we can define a function, right? A function that takes in an input x in W and outputs some morphism going from A to L assigned to that x, right? So maybe we'll call it theta. Theta goes from W into the home set from A to L. And it's defined by theta of x is equal to the unique phi x such that Lj after phi x is equal to Wjx. So we have found a function here that we called theta going from W into the home set from A to L. And what we need to know is, does this theta make all of these legs of our W cone commute with all of the legs of our image of our limit here? And, of course, it needs to be the only one that does that, right? Because this needs to be a unique mediating morphism. Well, this is for all j and j, so what we can say is if we plug this theta x into this formula, we have that for all j and for all x, so for all j and j and for all x and W, we have Lj after theta of x is equal to Wj of x. So we'd need to have that followed by Lj, right? That's what these components are, followed by Lj after theta would have to be equal to Wj for all j. So let's try plugging that in. So let's say for any j and for any x, what do we get if we do followed by Lj after theta and then apply that to some x and W? Well, then we'll get that we have Lj after theta x, right? We're basically just applying it to this, which means that we follow by, and then we would have that this would be equal to Wj of x. And since this side is equal to this side, we have that Lj followed by after theta is equal to wj. And this is the exact commutativity property that we needed, right? That's this, and it's for every j, right? So it applies to every leg. So every leg commutes, and the only thing we need left to prove is that it's the unique one that does it. It's the only morphism that commutes with all of these legs. But it is unique because there's only one way to define it, right? Because for any x in w, this equation means that theta of x has to satisfy this equation, and for each x, there's only one morphism that allows this equation to be true, right? That's what we said this unique phi was. So basically, every single time we grab an x in w, we only have one option, which is phi of x. And so what that means is that this unique mediating morphism is the cone morphism that we required, and that means that the image of L is in fact a limit over this diagram, the image of this diagram under the covariant home functor. So we've shown that the covariant home functor does preserve limits, and that's QED. So that's probably the most difficult of the three exercises. And the third exercise, as I mentioned, will be coming in a future video.